Hello everyone. In the previous session we discussed the application of a double and triple integral in finding the area and volume. Now in this session again we are going to discuss the application of a double and triple integral in finding the center of gravity. So before going to know the standard result of center of gravity, let me define what is the center of gravity. We should know what is the center of gravity, right? So center of gravity is a point in a body or in a system around which its mass or a weight is evenly distributed or balanced and through which the force of gravity acts. So that is called our center of gravity, and these are the examples for center of gravity. So ourself is an example. If we don't have a center of gravity in our body, we can't balance our body, and we know the standard we are all familiar with the seesaw. That is the best example for a center of gravity. Okay. So how to calculate the center of gravity now? The center of gravity of any object is calculated by taking the sum of its moments divided by the overall weight of that object, right? So we can calculate the center of gravity for the different shapes. As you seen in the slide, we can find the center of gravity for all this, and this is the way we can find. But in our syllabus we are supposed to find the center of gravity for a plane lamina. Then what is a lamina? Lamina is nothing but we are going to find the center of gravity over a thin layer or a plate of the given curve. Okay. So let me define that. That is, this is our lamina. If I consider in a coordinate axis x and y, if I consider like this, and this part is called as lamina, a plane lamina. So in this, if I consider this as a point P of x comma y, and there is a mass m will be the mass, and we have A as the area, and this is our region R. So let A be the area of a plane lamina having a density rho of a function of two variable x and y. So let P of x comma y be any point on the plane lamina. Then the total mass of that plane lamina is given by m equal to double integral of rho, that is a density, dx dy over that area, over the given area of the lamina. So the center of gravity x bar comma y bar of the plane is given by x bar equal to double integral of x into rho into dx dy over a given area whole divided by double integral of rho into dx dy over the given area, that is nothing but the total mass m. And similarly my bar is double integral of y into rho into dx dy over area A divided by double integral of rho into dx dy over the area A. If we have a Cartesian coordinate at the point x comma y as a Cartesian points, using a polar coordinates we can define, or we know the standard form of a polar coordinate, that is x equal to r cos theta and y equal to r sin theta. Then the center of gravity is given by x bar equal to double integral of x is replaced by r cos theta into rho, and we know that in a polar form dx dy is replaced by r dr d theta whole divided by m is nothing but double integral of r rho into dx dy is replaced by r dr d theta. Similarly y bar is given by double integral of r, y is nothing but sin r sin theta, rho remains as it is, dx dy is r dr d theta whole divided by again double integral of rho into r dr d theta over the area A. So this will be your standard formula to find the gravity in a Cartesian. Solve the next problem. Using double integration, find the center of gravity of a lamina of the shape of a quadrant of the curve, and the given curve is x by a whole power 2 by 3 plus y by b whole power 2 by 3 equal to 1. The density of the curve, or the density being rho, equal to k into xy, where our k is constant. So now we are supposed to get the center of gravity using again double integration. So consider the given curve and construct the given curve. The given curve can be represented in a Cartesian plane, and that is given by, so the curve will be in this order or in this shape, x y axis origin. So we are going to get the center of gravity in this part. Okay, so I name it as OAB, and we know that this is A and this will be our B. So let G of x bar y bar be the point or the center of gravity in the given lamina. So let G of x bar comma y bar be the center of gravity of the lamina OAB. So we are going to get the center of gravity here, OAB. Now since the curve is symmetric about both x and y axis, so no need to get both x bar y bar. I can get either x bar or y bar. Similarly we can conclude the other point. So to get the x bar or a y bar, of course we should know what are the limits of x and y. So from figure we can say that from figure x varies from 0 to a. So this point will be a comma 0. So x varies from 0 to a, and of course y will be a variable limit. Y varies inside the given region and it is a line parallel to y axis, and we know that that should be our curve. If I consider that curve, so that y varies from 0 to this curve, the curve is x by a whole power 2 by 3 plus y by b whole power 2 by 3 equal to 1. So if I simplify, I will get the function of x. So I call it as y of x. Instead of writing it as some number 1 minus x by a whole power 2 by 3 and so on, I consider it as a function of x. It is nothing but y of x, right? So consider x bar, or we know that the standard formula to get the x bar is x bar equal to double integral of rho into x into dx dy divided by double integral of rho dx. So we know the standard formula for x bar, that is x bar is double integral of rho x dx dy and divide by, of course the mass m is double integral of rho dx dy. Now substitute your rho, so that we have x bar equal to double integral of rho is given by k into xy, right? So I replace that by k xy into x dx dy divide by double integral of k xy dx dy over the required area, the given area. So I can cancel x, so that our x bar remains with double integral of x square y dx dy. So let me substitute the limit also. Now I can take out k common and I can cancel with k, and also substitute the limits of x and y, so that x bar is integral 0 to a, x varies from 0 to a, and y varies from 0 to y of x, and k can get cancelled. We remains with x square y dx dy whole divided by double integral of x varies from 0 to a and y varies from 0 to function of x, xy dy. So of course I have to write first dy and then dx, dy, dx, right. Now keeping x constant, integrate with respect to y, that is integral 0 to a x square constant, integral of y is y square by 2 between the limit 0 to a function of x, y of x dx. So now keeping your x constant, if I integrate with respect to y, we have x square into y square by 2 between the limit 0 to y of x dx. Similarly, if I integrate the denominator, double integral x constant, integral of y is y square by 2 between the limit 0 to y of x dx. If I apply the limit, we have integral 0 to a, so I can cancel 1 by 2 there, so that 0 to a x square into y of x nothing but y square dx whole divided by integral 0 to a, 1 by 2 get cancelled, we remains with x into y square dx. Now to evaluate this, we can replace the standard form of that polar form of that curve. The standard polar form of the given curve is, we know that x equal to a cos cube theta and y equal to b sin cube theta. We know that x equal to a cos cube theta and y equal to b sin cube theta is a standard value for any point, I will write here, for any point on the given curve. So we left with the dx only in the double line integral. So get the dx value here. Dx is given by 3 times of a into cos square theta into cos derivative minus sin theta d theta, or dx can be rewrite as minus 3a cos square theta sin theta d theta. So instead of keeping both x and y, because I left with y square, right, since I have not replaced y in terms of x, I will remains with y. So I substitute x and y in a polar form or a standard form of x and y for the given curve, so that I get dx. Now, so we got dx, right. So since we remains with x and y here, so I substitute or I represent the given curve in a polar form or the standard form. Now we should get what is the limit of theta, because we are replacing x and y in terms of theta. So the lower limit is 0. If x is 0, what is our theta? Theta is equal to, or cos cube theta is equal to x by a we have. So that if I replace x by 0, then we have cos theta equal to 0 or theta equal to cos inverse of 0, which implies theta equal to pi by 2. Cos inverse of 0 is pi by 2. And if x equal to a, that is the upper limit, then we remains with cos cube theta is equal to a by a nothing but 1, which implies theta equal to 0. Theta equal to cos inverse of 1, cos inverse of 1 will be 0. Now substitute the limit of theta and also x and y dx in the standard result, that is x bar, that gives you integral pi by 2 to 0, x is given by a cos cube theta, but we have here x square, so that we remains with a square, cos to the power of 2 whole power 3 is nothing but cos to the power of 6 theta into y square is b square sin to the power of 6 theta d theta into dx is given by minus 3a cos square theta into sin theta d theta whole divided by, the denominator is minus pi by, or integral varies from pi by 2 to 0, x is a cos cube theta and y is b, we have y square, so b square sin to the power of 6 theta, and dx is minus 3a into cos square theta into sin theta d theta. Now before going to integrate, simplify this. So since we have minus sign in both the integral, I can interchange the limits of integration so that I can remove the minus sign, and also I can cancel 3a and I can take out a square b square common in numerator and a b square common, so that b square get cancelled. We remains with only a. So x bar is integral 0 to pi by 2, or I will take a common, the remaining value 0 to pi by 2. So I interchange the limits of the integration because I remove the minus sign. So that we left with cos power 6 into cos square as a cos to the power of 8 theta into sin power 6 sin theta is sin power 7 theta whole divide by d theta whole divide by again the same thing. So here if I interchange the minus sign, we left with integral 0 to pi by 2 cos power 3 into cos square is nothing but cos to the power of 5 theta into sin power 6 into sin is nothing but sin to the power of 7 theta d theta. So now I can apply the reduction formula, the standard result. That is, the standard result is, we know that integral 0 to pi by 2 sin to the power of m theta into cos power n theta is given by is nothing but m minus 1 into m minus 3 into etc. into n minus 1 into n minus 3 etc. k whole divide by m plus n into m plus n minus 2 and so on, where k is given by pi by 2 if m and n are even and is given by 1 in other cases. So that k is replaced by either pi by 2 and 1. Pi by 2 is replaced, k is replaced by pi by 2 if both m and n are even. In other cases means if m and n both may be odd, and other case m is even and n is odd, or the other option is vice versa, that is m odd and n even. So the maximum we have 3 cases other than both are even. Now in this problem we have not both as even, so we have other option, or both as odd. So we have here both odd, and in this case one even and other one is odd. So I can use that formula, right? So using the standard reduction formula, we have x bar equal to a into, the numerator is m is 8 and n equal to 7 in the numerator. So that 8 minus 1 is 7 into 5 into 3 divide by into the first part. The second part is 7. So 7 minus 1 will be 6 into 4 into 2. So the denominator is 8 plus 7 is 15. So 15 is again odd number. So expand up to the least odd, 15, 13, 11, 9, 7, 5, 3, right, into k. K is here 1 because we have one odd and one even case, divide by the denominator now. So m value or n value is 7, right. So 7 minus 1, I can interchange that m and n, it is not an issue, right. So 7 minus 1 will be 6 into 4, 2, and the next term is 5. 5 minus 1 will be 4 into 2 divide by 5 plus 7 is 12. So 12 into 10 into 8 into 4, 6 into 4 into 2. So we have to expand up to the least even number, and that should be multiplied by 1 because both are odd numbers. Now simplify this. So I can cancel here 6, 4, 2, okay, and also I can cancel 4 into 2. and we can cancel 7, 5, 3, right. Now the remaining result is A into, this will go to numerator and this come to denominator, that is A into 12 into 10 into 8 into 6 divided by 15 into 13 into 11 into 9. Okay. So I can cancel these two. So that is using 3, 2s are 3s are, and also I can cancel 10 and 15, 5 2s are and 5 3s are, right. So and also I can cancel this 3 1s are, 3 4s are, right. So if I simplify the remaining values, that is A into 4 into 2 into 8 into 2 divided by 13 into 11 into 3, we have 128 times of A by 429. That is our x bar. Similarly, I can obtain y bar because curve is symmetric about both x and y axis. That will be similarly y bar will be equal to 128 times of b, because y by b whole power 2 by 3 we have, that is 128b by 429. Therefore, the center of gravity x bar y bar is given by 128a by 429 comma 128 times of a by 429 is the required result. Now the next problem is, the density at any point x comma y of a lamina is given, that is lambda by a into x plus y. So in the previous problem also they given you the rho value, here also they given you rho value, and also lambda and a are constant, and the given lamina is, the lamina is bounded by the lines x equal to 0, y equal to 0, nothing but x and y axis, and also x equal to a and y equal to b. Then in that lamina we are supposed to find the center of gravity. Okay. So construct the given curve or the get what is the given lamina. So using the given lines we can construct the curve, that is x and y axis and origin, right. So x equal to 0 is nothing but y axis, y equal to 0 is a x axis, right. X equal to a is a line parallel to x axis, y axis, and y equal to b is the line parallel to x axis. So this is our line y equal to b. So this is the required region or the area where we should find the center of gravity. Okay. So we should get what is the limit of x, right. So from the figure we can say that this is the point a comma 0. From figure we can say x varies from 0 to a and y varies from 0 to b. Now let g of x bar comma y bar be the center of gravity of the rectangular lamina OABC. Okay. From figure I can write from figure our x and y limit. X varies from 0 to a, it is clear, and y varies from 0 to b. So both are constant limit we have, right. Now consider, or we know the standard x bar formula. We know that x bar equal to double integral of rho into x into dx dy divided by the total mass, that is m is also given by double integral of rho dx dy. Now substitute the rho value and you know the limit of x and y. Substitute the limit of x and y and also the rho, so that x bar is integral 0 to a, integral 0 to b, x varies from 0 to a and y varies from 0 to b. and rho is lambda by a into x plus y into x dy dx whole divided by double integral of rho is lambda by a into x plus y dy dx, where the limits are x varies from 0 to a and y varies from 0 to b. Now, I can cancel lambda by a in both numerator and denominator, so that we remains with integral 0 to a, integral 0 to b. I can multiply x here, so that x square plus yx dy dx whole divided by double integral 0 to a, 0 to b, x plus y dy and then dx. Now, keeping x constant, integrate with respect to y. Okay. So, that is integral 0 to a x square constant dy integration y between the limit 0 to b plus x constant integral of y is y square by 2 between the limit 0 to b dx whole divided by integral 0 to a, same thing, keeping x constant, integral of dy y between the limit 0 to b plus integral of y is y square by 2 between the limit 0 to b dx. Now, apply the limit before going to integrate the next step and simplify. X bar is integral 0 to a. So, if I apply the limit, upper limit b, lower limit 0. So, I remains with x square b. In this next one also lower limit 0. So, remains with b square x by 2. So, we have x square b plus x b square by 2 into dx whole divided by integral 0 to a x b plus b square by 2 dx. So, I am not representing the lower limits there, right. Now, we left with only the x variable and also of course constant. Integrate with respect to x, that is b constant x square integration x cube by 3 between the limit 0 to a, b square by 2 constant integral of x is x square by 2 between the limit 0 to a whole divided by b constant integral of x is x square by 2 between the limit 0 to a, b square by 2 constant integral of dx is x between the limit 0 to a. Now, apply the limit and simplify, that is b by 3, and of course here also we have lower limit 0, right. If I apply or if I replace x by a, we have a cube b by 3 plus a square b square by 4 divided by a square b by 2 plus a b square by 2. Okay, now simplify this. So, in numerator I can take out a square and b common. So, that a square b common, here we remains with a by 3 and here we remains with b by 4. In denominator I can take out ab by 2 common. So, that we remains here with a plus b. Now, simplify that. I can cancel b and I can cancel a one time and that 2 goes to numerator, and if I take LCM between these two, we have 2 into 4a. So, I left with a also, 2a into 4a plus 3b by 12 whole divided by a plus b, or I can cancel 12 with 2 6 times. So, that we remains with a into 4a plus 3b divided by 6 into a plus b, which is our x bar. Now, okay. Similarly, I can obtain y bar. We know the formula for y bar. So, y bar is double integral of rho into y into dx dy whole divided by double integral of rho into dx dy over the given area. Now, replace your rho and also consider the limits of x and y, that is integral 0 to a x limit and integral 0 to b y limit, and rho is lambda by a into x plus y into y dx dy, or I have to write dy first and then dx, right, we know that, whole divide by integral x varies from 0 to a, y varies from 0 to b, and rho is lambda by a into x plus y dy and then dx. Now again I can cancel lambda by a here, right, so that we remains with integral 0 to a, integral 0 to b, xy plus y into y square, y into y square, dy dx, whole divide by integral 0 to a, 0 to b, x plus y dy then dx. Now keeping our x constant, integrate with respect to y, that is y bar is integral 0 to a x constant y integration y square by 2 between the limit 0 to b plus y square integration y cube by 3 between the limit 0 to b dx, whole divide by integral 0 to a x constant dy integration y between the limit 0 to b plus y integration y square by 2 between the limit 0 to b into dx. Now apply the limit and simplify, that is integral 0 to a, if I apply the limit again we have x b square by 2, so lower limit is 0 plus b cube by 3 dx, that is the numerator, whole divide by integral 0 to a x b plus b square by 2 dx. Now we left with only x and a constant, integrate with respect to x, that is b square by 2 constant, integral of x is x square by 2 between the limit 0 to a, b cube by 3 constant, integral of dx is x between the limit 0 to a, whole divide by b constant, integral of x is x square by 2 between the limit 0 to a plus b square by 2 constant, integral of dx is x between the limit 0 to a. Now apply the limit, that is y bar equal to b square a square or a square b square by 4 plus, if I apply here we have a square upper limit lower limit 0, I am not going to write the lower limit, so that a square minus or a square minus a square by 2 minus 0 will be a square by 2. So we have a square into b square by 2 2s are 4. Similarly here a b cube by 3 whole divide by, and in this case we have a square b by 2 plus a b square by 2. So as we simplified in x bar, simplify here, that is y bar equal to, I can take out a b square common, so that remains with a by 4 plus b by 3 divide by, I can take out a b by 2 common, so that we remains with a plus b. So I can cancel a and one time b, and if I take LCM between these two, y bar is b into 3a plus 4b by 12 whole divide by 1 by 2 times of a plus b. So I can cancel this 6 times, so that y bar is b into 3a plus 4b by 6 times of a plus b, that is our y bar. Therefore, what is the center of gravity x bar y bar? Center of gravity x bar comma y bar is given by the points, x is given by a into 4a plus 3b by 6 times of a plus b, comma, and y is given by b times of 3a plus 4b by 6 times of a plus b. That is the required center of gravity of the given rectangular lamina.